Hi everyone, today we're going to talk about black holes. This is what we've been building up to for a while, going through the stages of stellar evolution for low-mass stars and then for high-mass stars, including the ones that will eventually leave behind black holes. So, first of all, black holes don't suck unless you get too close, so they're not like these giant vacuum cleaners or anything like that. So, in other words, if you were to replace our sun with a black hole, well, things are still governed by Newton's law of universal gravitation. That's something that we're going to come to, and nothing would really change except for the fact that we would die because we wouldn't have the sun around. But there is something special about black holes. So, actually a lot of things special, which we're going to be discussing today. But let's examine the concept of escape velocity. There's a formula for escape velocity which you can derive by combining conservation of energy with kinetic energy and the real formula for gravitational potential energy to find that if you are at a distance r from the center of an object of mass m, or assuming the object's a sphere, then plug in this value of big G, which is a fundamental constant of nature, plug in the mass, plug in the r, and that will take the square root. You'll get the escape velocity, how fast you would need to throw the object in order for it never to come back. So if you were to plug in the mass of Earth and Earth's radius, you'd find that the escape velocity from the surface of Earth is 11.2 kilometers per second. But what if you were to shrink Earth? So remember that formula went as 1 over the square root of the radius? Well, that would mean that if you were to make Earth 1/4 of its size, the escape velocity would double. So it would become 22.4 kilometers per second. If you made it 1/100th of its size, then the escape velocity would be multiplied by 10, etc. And you could keep making Earth smaller and smaller and get higher and higher escape velocities. And as Earth becomes smaller, the escape velocity rises. But once you get Earth to a radius of about 8.8 millimeters, the escape velocity becomes the speed of light. Now, this is the concept of something that was known as a dark star. The concept was invented by this guy John Mitchell around 1783, and he basically went through an argument similar to what we just had. But in his idea, these so-called dark stars were situations where, okay, particles of light would end up kind of leaving the star, but then gravity would end up pulling them back. But we're going to see that that's not what happens in general relativity at all. They don't get pulled back simply because they never leave. They simply go inward. But we're going to get to that. So, in order to analyze the types of objects that would have these incredible mass concentrations, you've got to understand a little bit about general relativity. And, in fact, we already hit upon some of the general relativity concepts when talking about neutron stars and type 1a supernovae with white dwarf objects, and we needed to use some concepts with general relativity there as well. But in any case, when you get to a situation where the object is so dense that the escape velocity starts to approach the speed of light, you realize that space itself kind of starts to fold inward in a way, where all paths end up leading to the center once you have an object that has all of its mass within something called the Schwarzschild radius, which we're going to get to soon. And yeah, if you cross that distance, you cannot escape. The way that a lot of modern scientists think about it, they think of space itself as flowing into an object that has mass. And that's especially the case if most of the object's gravitational energy is embedded within the space, as is the case of a black hole, in which case all of its energy is embedded within space-time itself. So if you end up crossing within that Schwarzschild radius, you cannot escape. So it turns out that this also happens to be the distance where Newtonian physics, in other words, starting off with Newton's law of universal gravitation, tells us the escape velocity is equal to the speed of light. But that is the Schwarzschild radius, but it's special in many ways, more than just the fact that the escape velocity happens to be the speed of light at that particular distance. Now, again, that big G is Newton's gravitational constant. You multiply it by 2, multiply by the mass in kilograms. So the mass of our sun in kilograms is about 2 times 10 to the 30th, and divide by the square of the speed of light. So the speed of light being about 3 times 10 to the 8 meters per second. Now, let's see where this actually comes from. we're going to take a look at something called the Schwarzschild metric, which was one of the first solutions of Einstein's field equations. This guy, Karl Schwarzschild, got a hold of the report of general relativity while he was fighting on the Russian front during World War I, and in his spare time, he actually found a solution to Einstein's field equations, and he did this only a few months after the field equations were published. Einstein himself, by the way, figured that nobody would be able to find a solution to these field equations anytime soon. He certainly wasn't expecting it, I think, in his lifetime, but this guy did it in his spare time while fighting a war in just a few months. So here is the solution that Schwarzschild found. You don't need to memorize this equation. You don't really even need to understand it in all its detail or anything like that. You're not going to have to do any calculations with it or anything like that. I do want to highlight a couple of points about it, though. That 2gm over c squared thing that we've been seeing before for the escape velocity, it's there. It's part of the result of Einstein's field equations. In other words, even if the escape velocity wasn't equal to the speed of light at the surface of a black hole, like if we lived in some weird universe where that was the case, then you would still end up getting this term out. That's pretty cool. This little r is the distance from the center of your spherically symmetric object, in other words, a ball. And here's what we notice. As r gets smaller and smaller, once r becomes 2gm over c squared, you get 2gm over c squared in the numerator, canceling out with 2gm over c squared in the denominator. And that becomes 1. And 1 minus 1 is 0. What that tells us is that at that particular distance, somebody far away would observe time to stop. Time stops at the surface of these objects that we call black holes. Another thing, notice that if you were to plug that in down here, you'd have 2gm over c squared over 2gm over c squared. Again, that's 1. 1 minus 1 is 0, but this time 0 is in the denominator. You're dividing by 0, and as you know, only Chuck Norris can divide by 0. The result is that things end up becoming infinite. Space doesn't really make sense at what we call the event horizon of the black hole. This other stuff, these are angular terms that we don't really care about. But the point I wanted to raise is that, yeah, this 2gm over c squared distance becomes really important if you're able to come across an object in which all of its mass is within that value. Now, what about the case of Earth? We said that in the case of Earth, to get the escape velocity equal to the speed of light, Earth would have to have a radius of 8.8 millimeters. Well, what if you drilled toward the center of Earth? Would you end up getting a situation like that? Well, no, because once you reach the center of Earth, a distance within 8.8 millimeters of the center, that is, what you would find is that within that distance, there really isn't all that much mass. What's really important for gravity is how much mass is contained within the place where you are. And if you're at the center of Earth, there's not all that much mass contained within, say, like an imaginary sphere centered on Earth's center going out to where you are. But in the case of a black hole, all of the mass is within that distance. That's what makes a black hole really special. In fact, a black hole is defined to be an object in which all of its mass is located within its Schwarzschild radius. So that term was actually coined in 1968 by John Wheeler. He's a very famous physicist. He's one of the greatest minds of the 20th century and into the 21st. He actually lived to be almost 100 until he suddenly died of pneumonia, I think, in 2008. But he has a number of very famous graduate students, one of whom is Kip Thorne, who is now the world's foremost expert in black holes and general relativity. And Kip Thorne became famous a few years ago because he won the Nobel Prize. He was the leading theoretical collaborator in the LIGO gravitational wave experiment, and he was also somebody who became known to among the population because of the fact that he was the leading scientific collaborator of a movie called Interstellar. So a black hole is basically a point of no return. Once you go in, you can't go back out. No matter how much force you exert, you will not be able to increase your distance from the center of the object. And that's really the crux of it. Once you get within the Schwarzschild radius, it requires more than an infinite amount of force to be able to increase your distance from the center. If you're at this force-field radius, it requires an infinite amount of force. In other words, Newton's law of universal gravitation, that equation that I showed you at the beginning of this video, is not true near the surface of a black hole. It's only an approximation that's true a great distance away from the surface of a black hole. In fact, the general idea is that if you're within 10 force-field radii of an object, then you need to use general relativity. You can't use classical physics. And the general relativistic correction of Newton's law of universal gravitation tells you that at the surface of a black hole, the so-called surface, at the event horizon, the amount of force that would be required to hold an object there would be infinite. Whereas in the case of Earth, the amount of force required to hold an object above the surface of Earth would just be found by plugging in Earth's mass and the mass of the object and the distance from the center of Earth, that is, Earth's radius. But in the case of a black hole, it's more complicated than that, but at the force-field radius, that force becomes infinite. That's one reason, one of many reasons, why it's never possible to escape from a black hole once you go in. It would require more than an infinite amount of force. So we define the force-field radius kind of as, based on definition of black hole, as the boundary of the black hole. And you can go through, remember, so that 2gm over c squared bit for the force-field radius, that is proportional to the mass of the object, which means if you figure it out for one object, then all you need to do is multiply by the number of those types of objects you have to figure out what would be the force-field radius of that. So if you plug in the mass of our sun, you find that our sun's force-field radius is 2.95 kilometers. Well, that sounds awfully close to 3 kilometers. So, to figure out the force-field radius of an object that has x number of solar masses, the answer is 3 kilometers times x. So, in any case, general relativity. We need to talk about that in a little bit more detail before we continue. Einstein published this in late 1915. 2015 marked the 100-year anniversary of this, and this is based on something called the principle of equivalence, that on localized scales, the gravitational force is indistinguishable from uniform acceleration. In other words, if you are in an elevator that is accelerating at 9.8 meters per square second, that's Earth's acceleration due to gravity, 32.2 feet per square second, then that is indistinguishable from just being in a closed room on Earth. In other words, there is no experiment that you would be able to do within that closed elevator that would be able to allow you to distinguish between being there and being in a closed room on Earth. In other words, anything would fall at a rate of 9.8 meters per square second. Any other experiments that you would do would be in complete accordance with being on the surface of Earth. That is the crux of the principle of equivalence. And based on that, and on trying to find a coordinate-free representation of his special theory of relativity under the influence of gravity, Einstein eventually came up with general relativity. And the result of this is that a massive object bends or warps space-time around it, and that bent or warped space-time results in objects accelerating. John Wheeler, who, as I mentioned, invented the term black hole, stated it like this: mass tells space-time how to curve, and curved space-time tells mass how to move. So you can kind of represent this in the famous rubber sheet diagram. If you have a massive object there, it kind of bends the coordinates in this case. In this case, we made our coordinate grid such that it was centered on whatever object is here. And you can also think of this, if you have a rubber sheet, you put a paperweight there and it bends everything. And the realization here is that the shortest distance between 2 points is no longer a straight line. And this analogy has a number of problems, not the least being the fact that you're using gravity to show what gravity does. But in any case, you also need to kind of turn this into a three-dimensional view. And when you turn this into a three-dimensional view, which is very difficult to visualize in this case, visualizing curved three-dimensional space, what you realize is that, yeah, the shortest distance between 2 points near a massive object is not going to be a straight line. It's going to be some bent path around that massive object. So even if that massive object, even if you could completely go through that massive object, still the shortest distance would not be a straight line. So according to general relativity, satellites move in orbits around Earth because they follow the curvature of space-time caused by the mass of Earth. And the more massive the object, the greater the curvature is going to be. Now, I've been saying space-time. This has effects on time as well. For example, if you're going in Earth's orbit in the same direction that Earth rotates, time travels a little bit faster than if you try going in the opposite direction. We're going to come to that soon. That's frame dragging, or one of the effects of frame dragging. But in any case, there are lots of predictions of Einstein's general relativity. Now it's one of the most thoroughly tested theories in all of science. But still, we're trying to challenge general relativity further by analyzing situations where the gravity is extremely strong. We know it works in situations where the gravity is relatively weak, like say around our sun. I mean, most of us wouldn't consider that weak, but according to general relativity, yeah, that's weak because our sun's radius is much, much larger than its force-controlled radius of 3 kilometers. In other words, our sun has a radius of about 7 times 10 to the 8 meters, whereas its force-controlled radius is about 3,000 meters. That is 3 kilometers, or the actual radius being 7 times 10 to the 5th, or 700,000 kilometers. So we have, as I mentioned, found that not only does Earth bend space-time, but due to the Earth's rotation, it actually drags space-time around it. Now, some tests of general relativity that have been done have been the fact that it explains the advance of Mercury's perihelion. We're going to see what that means soon. It also predicts a certain amount of deflection of starlight around a massive body. It predicts slowing of time in the presence of gravity. It also predicts gravitational redshift, the fact that if a source of known light frequency or wavelength is being shown outward from a massive body, recipients of that light will observe the wavelength to be stretched. It'll be a little bit longer than what was emitted. And it also predicts gravitational waves from the decay of rotating things like objects and orbits of pulsars around each other, as well as the merger of black holes, something we're going to get to very soon. Now, what do we mean by the advance of the perihelion of Mercury? Well, Mercury, the innermost planet, is also the least massive of the official planets, and it's being affected by a lot of the other planets in the solar system, Jupiter in particular. And that causes Mercury's orbit not to be a perfect ellipse. It ends up shifting a little bit. But here's the thing. We can calculate those shifts. People were able to calculate those shifts back in the 18th century. Shift happens, and once they started measuring them in more detail in the 19th century, what they found was that they couldn't account for all of Mercury's motion. So, in other words, over time, Mercury does something like this, mainly due to the effects of the other planets, but there's an extra 44 arc seconds per century. Remember, an arc second is 1/3600th of a degree. That's really, really small, but it's big enough that astronomers were able to measure it in the 19th century. Well, meanwhile, Einstein didn't even really know about this to all that much of an extent. He wasn't incredibly familiar with the numbers here on that. I mean, he might have heard about it somewhere. But when he came upon his earlier formulation of general relativity in the early 19-teens, he made a calculation and found that this calculation is actually able to completely explain the missing 44 arc seconds per century of Mercury's perihelion shift. So that was pretty awesome. Now, also, general relativity predicts that light does not actually travel in straight lines. In other words, it ends up getting bent by the effect of a massive object. Now, here's the thing. Newtonian gravity, classical physics, would have also predicted that. In fact, people were making calculations based on this in the 1800s, long before Einstein. Well, yeah, he was born in 1879, but I'm talking about people were making calculations on this like around 1815, based on the prediction of Isaac Newton. But here's the thing. Once Einstein got his full version of general relativity complete, his prediction of the bending of light's path was actually twice as much as the prediction of Isaac Newton's general relative or classical theory of gravity. So this was eventually tested in 1919 by Sir Arthur Eddington. He was the main leader. The expedition that he led was to the Cape Verde Islands, I believe, to view a total solar eclipse. Now, Total solar eclipse is needed because, well, look outside at the daytime. During the daytime, can you see all of the stars around the sun? No, of course not, because of all of the light of our sun hitting our atmosphere and scattering off, and because of that, you can't really see the stars well. And also, our sun is really, really bright, so even if you didn't have the atmosphere around, it would still be rather difficult to see stars during the daytime. Now, during a total solar eclipse, that makes things nice and dark, and you can actually just barely see a few stars around our sun during a total solar eclipse. At least I was able to during the total solar eclipse of August 21st, 2017. I also saw the planet Mars right next to the sun. That was pretty cool. And Venus, which was farther away, was just really, really bright. In any case, what they actually witnessed in this case was at least consistent with the predictions of general relativity. I say consistent, well, here's the thing. The big newspaper headlines of the time were that this confirmed Einstein's theory. Well, not exactly, because the accuracy with which these observations were made was not sufficient to disprove Newton's theory. Yeah, it proved that the light bended around the sun, but it didn't show that it bent twice as much as what Isaac Newton was predicting. However, this experiment has been repeated lots of times, and it has been confirmed to a much higher degree of accuracy, and we know now that, yeah, the prediction of Newton's theory of gravity was wrong, the prediction of Einstein's general theory of relativity was right. And we can also realize that there's going to be a time slowdown as well, and that's something that we're about to get to. In this picture, this also shows the effects of bending of the light of distant galaxies around galaxy clusters. In this case, a lot of these pictures where you see these kind of weird shapes are actually distorted galaxies. They're distorted because of the bending of the light to begin with, but they're also multiplied. For example, this galaxy right here that you see is actually the same galaxy as right here. And physicists have confirmed this in some cases because there are special situations where, like, you'll say have a really massive galaxy right in front of a very distant galaxy, and the light of that distant galaxy is perfectly bent into multiple paths to surround, say, the galaxy that's in the foreground into multiple different images. And there have been some cases where a supernova goes off in the lensed galaxy, and we see that supernova at different times, slightly different times, because of the fact that, yeah, it's right behind it, but not perfectly behind it. So there are slightly different times in the light travel time. So you'll see the first event show up, and then a few years later you'll see other events show up. It's a really interesting verification that this actually does occur. Now, that time dilation that I mentioned, yeah, near a massive body, time slows down. Around the surface of the sun, gravity is 28 times stronger than on the surface of Earth. A result of that is that a clock will lose 64 seconds per year if it was sent to the sun. So if you sent an atomic clock, actually you don't even need an atomic clock on this, if you sent a quartz watch to the surface of the sun, assuming that it is able to survive the intense heat, and then brought it back to Earth, if you left it near the surface of the sun for 1 year, you would find that it has lost 64 seconds. Time on Earth is 64 seconds faster than the watch that you had near the surface of the sun. So it's not enough to make you live longer by being in the gravitational pull of a planet, but at least not any more than like seconds during your lifetime, but it's still an interesting result. However, it's also a result that is measurable even in short time spans. For example, when the Viking landers were on Mars in 1976, there was a time when Mars went directly behind our sun. From our point of view. And by directly behind, I don't mean 100% behind, but along the same line of sight, roughly speaking. And one result of that was that the signals that were being sent from the Viking landers were slightly delayed because of the time slowdown near the surface of our sun. So that's also pretty cool. Gravitational redshift. So this experiment has been done. They send a laser beam up from the bottom floor of a building, and when it gets to the top floor of the building, the beam is slightly redshifted. In other words, if the beam had a wavelength of, say, 400 nanometers at the bottom, then at the top it might have had a wavelength of 400 point something 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 greater than 0 nanometers. So that's also a nice verification of general relativity. Now, as the mass increases, the space-time curvature becomes larger and larger. So let's consider a star shrinking to become a black hole. Now, before we do that, I also want to mention some other results of this having to do with frame dragging. The geodetic effect and the geodesic effects are results that are predicted due to the fact that as Earth is going around the sun, Earth is rotating, and that drags space-time around it. And satellites that are in orbit around Earth will have their axes of rotation, like if they have gyroscopes on them, very careful gyroscopes, those axes of rotation will slightly shift due to the effects of this frame dragging. So that's also another cool result. In any case, a star shrinking to become a black hole. First, light will be able to escape from the star in a straight line regardless of which direction the beam comes from, but as it shrinks, the gravity increases and the space becomes more warped. As a result, that light beam ends up getting significantly redshifted. If you had light going not directly outward from it, that light beam would be very significantly curved. In the case of a neutron star, which is kind of the last step before a black hole, you add more mass, enough mass to a neutron star, it's going to collapse to a black hole. That curvature is very severe. In fact, the time dilation there is pretty significant as well. If you were on the surface of a neutron star, 1 second according to you would be like 2-point-something seconds according to people on Earth. It's quite significant there. So, in any case, as you get closer and closer to a black hole, the curvature becomes more severe. And if you made your star just barely larger than a black hole, then rays of light that are pointing directly outward would take paths that come just about to landing back on the surface of the object, and they would have to be pointed exactly outward to prevent that from happening. If you're, say, just a little bit directly outward from the object, the beam of light is going to come back to the surface of the object. And then, once it shrinks below the Schwarzschild radius, these light rays that are at the event horizon, if they're shot, quote, outward, then they would actually end up moving horizontally and then fall into the event horizon. Now, there is a common misunderstanding out there that a black hole is an object in which the escape velocity is greater than the speed of light. That actually is true, but that's a coincidence, as I've mentioned before. If we lived in some weird universe in which the escape velocity of a black hole was less than the speed of light, it still would not be possible to escape from the event horizon of a black hole. The Schwarzschild radius is something that's quite special, and it has an effect on the surrounding space, preventing any objects from within from coming out. I already mentioned that it would require an infinite amount of force in order to hold something stationary at the Schwarzschild radius. An infinite amount of force, which would mean it would also require an infinite amount of force for it to be able to move at constant velocity, either one way or the other. So inside of the black hole would require more than an infinite amount of force in order to get something to increase its distance from the center. Well, that's just not possible. It doesn't even make sense. What's more than infinity? So you can't do that. Another thing is that, remember that Schwarzschild metrics that I showed you before? I mentioned that time stops at the edge of a black hole. Well, that's according to distant observers. If something was at the edge of a black hole and it started trying to flash beams at you or something like that, an infinite amount of time would pass on Earth before we would be able to observe those beams. In other words, it would take an infinite amount of time to observe something emerging out of the black hole. Well, therefore, that's also not possible. I mention this in particular because there is this mistaken notion that you sometimes hear that, yeah, maybe if you fired a rocket that had sufficiently strong engines, that you were able to get it to a distance away from the center of the black hole where the escape velocity is less than the speed of light, then maybe it would be able to escape. No, no, no. That is completely misunderstanding the fact that general relativity is completely different from classical physics. That's a classical physics type of argument, and we know that classical physics breaks down near a black hole. I mention this in particular because Bob Berman, one of the main authors in Astronomy Magazine, has repeatedly mentioned this as a possibility, but it is not possible, no matter what you try to do, for, again, multiple reasons. One, it requires more than an infinite amount of force. Two, there is no outward direction of space. Three, the time stops at the edge of the black hole in any case. So lots of reasons why it's not possible to get something to escape from inside of a black hole. So there's again our curvature due to a low mass object, but for a high mass object like a black hole, we realize the space-time curvature is so great that it's such that space itself is practically, well, I shouldn't say practically, literally flowing in a direction toward the black hole at that point, at the speed of light. Farther away, not so much. Farther away, it's possible to escape. But once you're at the source shield radius, it's going at the speed of light. That's yet another reason why you cannot escape from a black hole, because the direction of the speed of the flow of space toward the center of the black hole is equal to the speed of light at the source shield radius. Inside of the source shield radius, it's actually greater than the speed of light. Yeah, I know Einstein's special relativity tells you can't travel faster than the speed of light, but that's talking about you can't move an object through space faster than the speed of light. But space can do whatever it wants to, so it can move faster than the speed of light relative to other reference frames. So in any case, yeah, there is this flow of space traveling at the speed of light at the event horizon of the black hole. So what about our collapsing star? Well, from the point of view of general relativity, it shrinks forever down to a singularity. But in truth, to figure out what really happens, we need a quantum theory of gravity. So remember, quantum mechanics is something that talks about what happens on very small distance scales, how you cannot get an extremely well-defined position for something due to the uncertainty principle and other effects, that sort of thing. But general relativity tells you what happens in the realm of very high mass. Quantum mechanics and general relativity, unfortunately, do not play well together. But what happens in the middle of a black hole, you need something that combines quantum mechanics and general relativity. And even though we have a number of potential theories, things like superstring theory, we're not sure that they actually describe our universe. So whether they actually apply to us, we don't know. But that's, even though a lot of scientists might not like superstring theory, they still investigate it, because even if it doesn't describe our universe, it still probably gives us insight to figuring out what's going on in regimes like near the center of a black hole and that sort of thing. Now, mentioned before, black holes don't suck. In other words, if you're far enough away, it's not really going to do anything. If you replaced our sun with a black hole, Earth would still exist. We would keep going around the sun in an elliptical orbit, the same orbit that we currently have. We would all die, of course, because, well, I mean, we kind of need the light of our sun in order to exist. But without that energy source, we wouldn't have anything. But we'd still be in orbit around the sun. Earth would not get pulled in. So Newton's law of universal gravitation, in other words, still works here, because you are much, much farther away than the source shield radius of our sun. Remember, the source shield radius of a one solar mass star is 3 kilometers. Well, Earth is 93 million miles away from the sun. That's about 150 billion kilometers. Or sorry, 150 million kilometers, 150 billion meters. So, still, everything in our solar system would continue in its present orbit. So why are black holes so scary for a lot of people? It's because of the fact that all of the mass is within the source shield radius, which means that it's possible to get really, really close to the source shield radius without colliding with the mass. What if you tried to get toward Earth's source shield radius of 8.87 millimeters? Well, I'm sorry, you would smack into Earth. That's a problem. So you can't do that in that case. But in the case of a black hole, all of the mass is within the source shield radius, and they often tend to be really, really massive, so their source shield radii can be relatively big. And the result is that if you get close to that, say like with a normal star going into orbit, that star can get pulled apart because of tidal forces. So this is actually what things would look like around a black hole. This is not just an artist's impression. This is a result of a detailed computer simulation with a galaxy as the background here. So kind of your line of sight between the black hole and the galaxy. And if this looks familiar, there's a reason for this. Image credit, the Interstellar movie team, which included a lot of their scientific collaborators, and of course Paramount Pictures, which was the producer. But yeah, Interstellar, actually, at the time that Interstellar was produced, the images and videos that it had of the black hole gargantua were actually the most scientifically accurate reproductions of the environment of around a black hole that had ever been created. So there was a lot of scientific research that came out of trying to make Interstellar. They got new scientifically important results due to the need to create this movie and try to get it as scientifically accurate as possible. So that itself is kind of cool. Now, these tidal forces that I just mentioned. We've mentioned tidal forces in the class before, and the overall result, remember, is that because objects that are massive also tend to be macroscopic. What that means is that, remember Newton's law of universal gravitation, even in that case, tidal forces are important. I mean, we call them tidal forces because they're similar to what causes Earth's tides. It's the gravitational force of our moon. In the case of our moon, the near side of Earth is accelerating toward our moon in the orbit, of course. I mean, things that are in orbit are accelerating. It's just they're also moving tangential to the acceleration. But the near side of Earth feels a stronger force toward the moon than does the central part. So the oceans on that side are kind of pulled a little bit more strongly. The central part of Earth feels a stronger force than the far side of Earth. So the central part of Earth is pulled more strongly than the far side. That's why you get 2 high tides per day, one from the near side, one from the far side, as Earth rotates throughout that. So, in any case, though, near a black hole, these tidal forces can rip apart stars. And these ripped apart stars tend to have a lot of very high energy material that ends up going into orbit around this black hole. And this high energy material can heat up to very, very high temperatures. So you don't want to be in that type of environment. Now, some properties of these black holes. Well, here's the thing. Black holes, believe it or not, are actually the simplest objects in nature. They can be described completely by just 3 properties, and really 2 in reality. Mass, electric charge, and angular momentum. Mass, you know what that is, how difficult it is to accelerate an object. Electric charge, you kind of know what that is. And angular momentum is basically a combination of the object's mass, how that mass is distributed, and how fast the object is spinning. Nothing else describes a black hole. And in truth, it's really only mass and angular momentum that really describe the black holes that tend to occur in nature. Now, I already mentioned that fact that because of the fact that the force-field radius is proportional to an object's mass, then you can just plug in the value of big G, the mass of our sun, and the speed of light squared, and realize that, hey, since it's proportional to mass, just work out those other numbers, and you get that the force-field radius must be equal to 3 kilometers times the object's mass in solar masses. That's a cool formula. Let's actually run a practice problem. Calculate the force-field radius of the black hole at the center of the Milky Way galaxy. That black hole has a mass of 4.5 million times the mass of our sun. Well, there's our formula. Plug in 4.5 million in there. Technically, I should be plugging in m equals 4.5 times 10 to the 6th solar masses, where this is the symbol for solar mass, but my m solar in the numerator cancels out with my m solar in the denominator, leaving this unitless, and the result ends up being 1.35 times 10 to the 7 kilometers. That is about 9% of the distance from Earth to Sun. That's a big black hole. In fact, it's what we call a supermassive black hole. We're going to say more about that one soon. If you were to imagine the planets as black holes, this would be their diameters. And again, these are diameters, not radii, so Earth's force-field radius is about 88 millimeters. Sorry, 8.8 millimeters. And so multiply that by 2, you end up getting actually 1.76 centimeters. So I think that just some rounding differences there. In any case, yeah, the bigger planets, or the more massive planets at least, have bigger force-field radii. In other words, in the case of Jupiter, we're talking about something that has a force-field radius of over 5 meters. But Jupiter's a lot bigger than 5 meters, so Jupiter is not a black hole. What about charge? Well, we actually don't think the black holes in nature really have any significant charge. So, why do you think that might be? I'll give you a moment to think about why black holes in nature don't have significant charge. Maybe pause the video to think about that. So if you have your answer, or if you are curious what the answer is, the reason is because if black holes did have charge, they would quickly attract opposite charges, and that would end up balancing things out. So black holes in nature do not have significant charges. Nonetheless, astrophysicists often pretend that black holes have charge and pretend that they don't rotate, because it turns out the result of a charged black hole results in very similar behavior as a rotating black hole. And the mathematics is easier for a charged black hole. That was worked out in 1919, but we didn't figure out how to deal with rotating black holes until 1963. Angular momentum, that's your rotating black hole. And believe me, black holes are rotating. That's one of the reasons why it's so difficult to simulate these things, because when you deal with rotating objects, you're dealing with something called the Kerr metric, which is a lot more difficult to deal with than the Schwarzschild metric that I showed you before. I'm not going to bother trying to show you the Kerr metric. It's hard. In any case, this rotation affects the surrounding spacetime. It endows the spacetime around the black hole with energy, rotational energy from the black hole. And the result is that frame dragging. I've talked about that frame dragging already. And if an airplane goes around Earth in Earth's direction of rotation, then that clock is going to run a little bit faster than if it goes around Earth against Earth's direction of rotation. And this effect has been tested not only with airplanes, but also with satellites as well. And as I mentioned, the axis of rotation of satellites also shifts because of the effects of this frame dragging and the effects of the orbital motion, showing that space-time really is kind of a real entity, and it's a real entity that bends. And nowadays, most general relativistic physicists think about this diagram as implying that there kind of is an extra dimension of space that the bending goes into. We can't directly observe that dimension, but it kind of goes into that in terms of the bending. So, what does this mean for black holes? It means that there's an additional concept known as an ergosphere that actually has importance. I should mention that all black holes have this entity called an ergosphere. It's just that with non-rotating black holes, the ergosphere is rather boring. It's just kind of this imaginary little spherical shell that surrounds the black hole. It's perfectly spherical. What's the importance of the ergosphere? The ergosphere is the region outside of a black hole's event horizon where it's still possible to escape, but in order to escape, you need to fire your rocket engines somewhat parallel to the event horizon. If you try to fire them directly outward, you're not going to escape. You're going to fall in. But if you fire them kind of parallel and acquire some tangential velocity that way, then you'll be able to escape. Now, with a rotating black hole, we think of this as the idea that in the ergosphere you cannot fight against frame dragging. In other words, if you try to remain motionless with respect to a distant star, you're going to fall in and you're going to die. So you can't fight against frame dragging for too long. Instead, if it's a rotating black hole, what you need to do is you need to fire your rocket engine so that your rocket goes in the direction of the black hole's rotation, and then you'll eventually be able to escape. Now, in the case of a maximally rotating black hole, one that's rotating as fast as it possibly can, at least under the guidance of general relativity, the ergosphere, colored in blue here, has kind of a weird shape, which I think is kind of cool. If it's not a maximally rotating black hole, then the points of the ergosphere don't actually meet the poles at the black hole's axis of rotation. Notice something else in here. The singularity. It's not a point. It's not a line even though it looks like that in this picture. It's actually a ring. A rotating black hole has a ring singularity. Now, some interesting consequences of that ring singularity. I don't want to get into this in too much detail because most of this probably doesn't actually work out, but it is at least theoretically possible that you might be able to travel through a wormhole that goes through the middle of that ring singularity. That wormhole would potentially take you back in time, either to an earlier time somewhere else in our universe, or into another universe entirely. There are some really cool videos that show what that might look like. Just either go to YouTube or actually Google Andrew Hamilton. He's a professor at the University of Colorado. He's made a number of simulations involving going into a black hole. We're actually going to talk a little bit more about going into a black hole later on, but in Andrew Hamilton's simulations, he also considers the possibility of actually traveling through one of these wormholes and shows what that would look like. Another way of experiencing what that would look like would be to watch the movie Interstellar. It is, to the greatest extent possible, scientifically accurate in terms of what could happen. Now, in reality, the wormhole would probably collapse as soon as you try to send something into it. These wormholes are unstable unless they happen to be threaded with some sort of exotic matter that has negative energy and negative pressure. So, we do know of things that have negative energy. The cosmological constant is an example. It also has negative pressure. But the cosmological constant, we believe, also has maximal entropy, which means you can't use it for anything. Now, something else about black holes is something called the cosmic censorship conjecture. We do believe that it is true with the black holes that exist in our universe. The cosmic censorship conjecture is, stated long story short, there's no such thing as a naked singularity. In other words, a singularity of a black hole must be hidden by a black hole's event horizon, clothed by the event horizon, so to speak, such that it cannot interact with the outside universe. Now, theoretical physicists, being theoretical physicists, have found a few pathological solutions of Einstein's field equations that violate the cosmic censorship conjecture. However, those pathological situations are black holes that cannot exist in our universe. Things like cylindrical black holes and that sort of thing in a rotating universe and weird things like that. So another way of stating this is that God abhors a naked singularity, the cosmic censorship conjecture. So in other words, you cannot have the singularity of a black hole, the central thing, unless you have an event horizon. Now, let's take a look at some examples of black holes. So the first highly recognized black hole candidate was the object called Cygnus X1. This was a famous X-ray source. It's in the constellation Cygnus. X1, the brightest X-ray source in Cygnus. And this is a situation where you have a star, HDE 226868, that is the 226,868th star in Henry Draper Extended Catalog of Stellar Sources. This star has a mass of somewhere between 17 and 21 times the mass of our Sun. It's orbiting around an object that has a mass of somewhere between 14 and 16 times the mass of our Sun. Now, as we learned in the discussion about neutron stars, the maximum possible mass of a neutron star, even if it's rotating as fast as it can be rotating, is 2.9 times the mass of our Sun. Well, when scientists looked at this system through optical telescopes, they found the star, but they didn't see anything at where the other mass should be. So that's kind of weird. So here's an artist's impression of this. This is the star HDE 226868 and the black hole in orbit around each other. Notice that in this case, the black hole is close enough to the star that the tidal forces are able to start pulling material off of that star, which is why there's this nice accretion disk around the black hole, which is why the X-rays are being created to begin with. Because once you get close to here, we're talking about temperatures that start to approach 100 billion kelvins, as depending on the black hole and everything. But billions of kelvins, yeah, you're going to be radiating in X-rays and gamma rays and stuff like that from this accretion disk. Now keep in mind, the jets that come out of this area that end up beaming toward radio telescopes and X-ray telescopes and that sort of thing, the jets are not directly coming from the black hole. They're coming from the accretion disk. The accretion disk, since you're dealing with charged particles in very fast orbit around something, that creates very strong magnetic fields. Those magnetic fields corral more charged particles, which end up creating jets. In any case, what we know about Cygnus X1 is due to something called the radial velocity method, and I don't have it for you right now for this, but if you happen to have the great course called, that is from the teaching company, The Great Courses, called Black Holes Explained, they explain the radial velocity method very nicely in Lecture 4 from about 4 minutes to 6 minutes and 20 seconds. So here's kind of an artist's impression of how this would be around a black hole. The smallest known black hole candidate is actually only about 3 times the mass of our Sun. It's believed to be responsible for a series of pulses emitted from the region near another black hole, and if you had access to this hyperlink, if I remember to, I'll try to post it in the video link, then you can actually see a video of this process. Other examples of black holes. The first universally accepted example is around the black hole at the center of M87, the very, very large galaxy. It is at the center of the Virgo supercluster. If you're a galaxy that's at the center of a galaxy supercluster, you're probably a really large galaxy, and that is definitely the case with M87. It has several trillion stars, and it also has a black hole that has a mass of 6.4 billion times the mass of our Sun. I remember when this discovery was announced in May of 1994, my 7th grade teacher, shout out to Miss Birdseye, showed me a picture, showed me a newspaper article about this announcement about the black hole at the center of M87. I remember back then they figured that its mass was only like 3 billion times the mass of our Sun. Only 3 billion. Now we realize it's 6.4 billion times the mass of our Sun. Here's a picture of M87, a really incredible galaxy. It's almost perfectly spherical. You have a bunch of these dots here. These dots here are not Milky Way foreground stars. Most of these dots are actually globular clusters, clusters of typically like hundreds of thousands of stars, all tightly knit within a sphere that's maybe only 100 light years wide. But the Milky Way has a couple hundred of these things. M87 has 10,000. It's over 9,000 globular clusters. Notice the center of it, though. Coming from the center, there's this jet. This jet coming from the center was discovered around the beginning of the 20th century as telescopes became better and better. And if you zoom into that with the Hubble Space Telescope, this is slightly zoomed in, you see that, yeah, there's really something quite interesting about this that's very different from the light of these several trillion stars of the rest of the galaxy. And notice all these globular clusters that you can see here as well. If you zoom in even more with the Hubble Space Telescope, you realize that there's a central region there that has very fast-moving gas. And if you take a spectroscope to analyze the Doppler shift of the light in different parts of this disk, you find that on one side of this disk, the light is coming toward us. The light is blue shifted toward us. The wavelengths are compressed. And on the other side, the light is red shifted. The wavelengths are extended. And the degree of the red shift versus blue shift, notice the wavelength down here, the shift between this, the wavelength difference is what allows scientists to determine the mass of this black hole. In this case, determination being 6.4 billion times the mass of our Sun. Here's another image of this thing. This became big news back in the middle of 2019. The image of the area around the M87 black hole. This was taken using the Event Horizon Telescope, which is a network of radio telescopes spread throughout the world and linked together in their communication such that they get the same angular resolution as you would have for a telescope that's about the same size as Earth. Well, Congress isn't going to fund a telescope that's the same size as Earth, but by getting the supercomputers to work out everything with all the communication details and the signals between these radio telescopes, we get the same angular resolution as a telescope that would have the size of Earth. You obviously don't get the same light gathering power because you need to have a dish the size of Earth in order to get that, but you get the same angular resolution. And in this situation, it's the angular resolution that you care about. We don't care about the light gathering power so much. In any case, what do we see here? This ring is actually the ring that's kind of emitted by the light that is in orbit around the black hole. And the inner edge of this ring is the light that's actually kind of starting to fall in here. This inner part here, this black dark area in the middle, that's not the black hole itself. It's not the event horizon itself. It's actually what you can think of as kind of the shadow of the black hole's event horizon that's being produced because of the light that's in orbit around the black hole. It's what we call a light ring, and again, we're talking about very hot gas here that's resulting in this light ring itself. The gas itself is farther out, but you can kind of imagine how this is being produced in this diagram right here, where you have the light particles, the photons, some of which end up escaping that area, being bent by the gravity and into this type of shape. So the ring that we see, we're kind of, Earth is to the right in this top image, and the ring that we see is from looking down in this direction. Pretty cool. So here's a zoom into this, and compare it with our solar system. So remember, the radius of a black hole goes as the black hole's mass. It's proportional to the mass, and take the mass in solar masses and multiply by 3 kilometers. Well, here we're talking about a 6.4 billion solar mass black hole. Multiply that by 3 kilometers, you're talking about 19.2 billion kilometers for the radius of this black hole. So that's like 12 billion miles. So, I mean, just round Earth's distance from the Sun to 100 million miles. The distance from our Sun to Pluto is about 40 Earth-Sun distances. That is 40 astronomical units. So 100 million times 40 becomes 4 billion. You're still talking about only a fraction, about 1/3. About 1/5 of the radius of the event horizon of the M87 black hole. So that's a really, really giant black hole. So it's like the size of our solar system. Pictures of this were taken at different times over a span of several days, and you can see that from picture to picture there are some slight changes in this due to different mass concentrations emitting different amounts of light that end up falling into this light ring around that black hole. Now, in terms of black hole spectra, here's another situation, M84, which is another very massive galaxy kind of near the center of the Virgo cluster, which is the central cluster of the Virgo supercluster. M84 is kind of close to M87 in proximity, and it has something like a 1 billion solar mass black hole. And notice that if you make a spectrum of the light from one end of the central region of that black hole to the other end, as you get closer and closer toward the middle, the light is coming toward us faster and faster and faster and faster until suddenly there's a very, very big shift toward the light going away from us really, really fast after you have crossed the middle of the sample region. In other words, once you've crossed the area where the black hole is in your view. What about other black holes? Well, the nearest large galaxy to the Milky Way is the galaxy M31, the Andromeda galaxy. The center of that has a black hole that has a mass of at least 30 million times the mass of our Sun. I've seen estimates of that as up to like 70 or 80 million times the mass of our Sun. Bode's galaxy, which is another very nice galaxy that's not too far away, at least as galaxies go. It's 13 million light years away from us. You can see it in binoculars. In fact, supposedly some people with really, really, really good nighttime vision have been able to see M81 with their unaided eye from extremely dark locations. I've never seen it, though. I have seen it easily in binoculars, though. But in the constellation Ursa Major, near the Big Dipper, this galaxy, the central part of this galaxy has a supermassive black hole with a mass of 70 million times the mass of our Sun or more. Now, what about our galaxy? The Milky Way galaxy, we've mentioned its black hole before. It has a mass of about 4.5 million times the mass of our Sun, and the source is called Sagittarius A star. That's radio astronomy notation. So the Sagittarius A star, it is the brightest A radio source in the constellation Sagittarius. And so here's kind of a little map of our Milky Way. So here's our Sun, where our Sun is, and toward the center of our galaxy we have the location of that black hole. Here's the general environment here. This is an infrared picture, and using far infrared imagery you see the central area, the Sagittarius A star. Notice the object that's there. Oh wait, you can't see an object there. It's a black hole. But it is possible to map the motions of stars that go around that black hole. And that's exactly what Andrea Getz's group did starting in the 1990s. They mapped the motions of stars around this black hole, and they made a really cool video of this, which I'm going to show you now. So this is a YouTube video of that. I just started it over. Here's a star going around. Here's one coming in way over here. Watch this one. Here it comes real fast. Goes whee! And then it comes out again. Here's another one. Goes around. Goes whee! So we have a number of stars that are in orbit around this thing that allow astronomers to, based on Newton's law of universal gravitation and basically Newton's version of Kepler's third law, figure out the mass of this thing. Let's just see this again. So there's that star that just swung around. Here's this one coming in really fast, coming around, go real fast, go whee! And then this other one coming in starts going faster, faster, go whee! And it's really just an awesome result that they got that confirmed that, yes, there is the closest approach of this star that came out here was only like, I think, a few hundred astronomical units. So we're talking about something that is noticeably smaller than the overall scale of our solar system, but has a mass of 4.5 million times the mass of our sun. So that's the video that I just showed you. Now, what about how do black holes behave? Something that we're going to discuss when we talk about other galaxies and cosmology is that they can play a major role in the behavior of the galaxies in which they inhabit. So they can be very strong X-ray sources. Here's kind of a zoom in using X-ray light from the XMM Newton Space Telescope of the black hole at the center of M31, the Andromeda Galaxy. And yeah, there's bright X-ray source there as well. They can also quench star formation in not just the galaxy, but the entire cluster of galaxies if it's a very active black hole. That active black hole can shoot off these jets that end up ionizing all the surrounding gas, and the surrounding gas, once it's ionized, it can't go into forming stars. So that's also another important consequence of this. So recent research shows that many very distant galaxies have these objects as well. Very distant galaxies that, since it's very distant, say 11 billion light years away, that means that we're observing that light as it was emitted 11 billion years ago. So we are observing the universe 11 billion years ago. And remember, astronomy is the only field in which it is possible to directly observe the past, as opposed to simply observing relics of the past. So, in any case, yeah, there are supermassive black holes in galaxies that formed only a couple billion years after the Big Bang. And some of these things are so massive that it's kind of difficult to explain how they could have formed simply from the collapse of a massive star and then that little black hole accumulating together more mass by gobbling up other stars and other black holes and that sort of thing. They seem to have formed too fast. So another idea for how some of these early black holes might have formed, that is indeed how some of the supermassive black holes at the centers of galaxies may have formed, was simply the direct collapse of a very large, massive region of gas. So that's a subject of ongoing research, and we do not currently know for sure exactly how these early black holes formed. Maybe it was the collapse of a really big cloud of gas, or maybe it actually was a bunch of really massive stars that all blew up, left behind black holes, and those black holes merged together. The jury is still out. So where are some other black holes out there? In the 1960s, physicists observed these weird objects called quasars, which is just kind of a shortened form of quasi-stellar radio source. What these were is when scientists looked at kind of these stars, that certain stars, or at least star-like objects, they found that with radio telescopes they were very powerful radio emitters, but when you just looked at them with optical telescopes, they looked like stars. So they started getting interested, and they started taking some spectra of these things, breaking the light apart into its various colors and components, and some of the spectral lines they analyzed, particularly looking for lines for common things like hydrogen and helium, but instead they noticed that these spectral lines from these quasi-stellar radio sources were just weird. They weren't like anything that they had found before. But eventually they realized that actually these are hydrogen lines, just shifted by a lot, which meant that these things are coming from cosmological distances. In other words, distances over which during the light travel time the universe has expanded by a considerable amount compared with when the light was emitted, which is why the wavelengths were stretched to such long wavelengths that were not otherwise recognizable. So eventually observations have shown that these things are actually extremely active centers of active galaxies. And it was the Hubble Space Telescope in particular that completely made this case. So here's a picture of a quasar. In fact, I think this particular one is the quasar 3C273. And again, it looks like a point source of light. But when you blot out the point source, you realize that there's some structure around there. And this gets rid of the idea that, oh, maybe these things were the ejected black hole cores of active galaxies that just happen to be ejected from nearby, and that they were ejected at a very high speed and thus traveling at a high percentage of the speed of light. That was actually one of the theories that was out there. It was particularly hailed by the famous astronomer Houghton Arp, that these quasars were not cosmological distances away. He thought that they were actually close by, and he he supported that by the fact that a lot of these jets that come from these things tended to be linked to other galaxies. It turns out, though, that statistically speaking, you expect that to happen occasionally, because, I mean, you go in any direction, say from this, you're eventually going to come upon a galaxy. And what do you mean by linked? Well, it just depends on whether there's really anything there. I mean, here's a jet that does not appear to be linked to any galaxy in this particular picture. But in a lot of cases, they are, but that's really just a result of statistics. Also, if these things were ejected from the cores of nearby galaxies, you would occasionally expect to have some of these things traveling toward us at a high percentage of the speed of light. But in truth, all of them are traveling away from us at a decent percentage of the speed of light due to cosmic expansion. Here's another picture of one of these, and again, in this case, even without blotting out the central star, or sorry, the central quasar, so to speak, you see that this is actually the result of a recently merged spiral galaxy. In fact, most quasars are at the center of spiral galaxies. Spiral galaxies are galaxies that still have a lot of gas. They're still in the stages of star formation, and a number of these things are actually in the centers of recently merged spiral galaxies, meaning that, yeah, you have a lot more gas there. Gas is getting thrown into the black hole itself, which is what this thing actually is. We realize now that these quasars are the result of a supermassive black hole at the center of a galaxy. It's either in the process of tearing stars apart, or it's actively feeding on gas in a very gaseous galaxy. And spiral galaxies tend to have a lot more gas than do elliptical galaxies. We're going to discuss in a future unit why that's the case. In other words, if you have lots of gas, that tends to kind of smooth out stellar orbits, whereas if you don't have much gas after a collision, then the stellar orbits are going to just remain in that same orientation. And in any case, as these black holes are feeding off of this gas, remember, you're talking about going from a larger distance into a black hole, which is what we call a very, very deep potential energy well. There's a huge conversion of gravitational potential energy into kinetic energy. And as this spirals around, it ends up hitting other gas particles, causing them to heat up, and you get lots and lots of energy out of this accretion disk as it is. And this is all ionized material. It's plasma, and plasma that's moving very fast generates very strong magnetic fields. These magnetic fields, we've mentioned this already, end up focusing beams of material, and you end up getting these jets that come out of this. So now that we realize that we're dealing with these jets, maybe we can start to have a a better understanding of what these things really are, and maybe unify this with another picture of what we have. So here's an artist's impression of a quasar with its jet. So here's the general idea. And I have slides explaining this in more detail, but I'll just kind of mention it here with this picture. Let's say you have this quasar here, a black hole that's actively feeding on gas. If you're looking at this, say, from along the disk itself, edge onto the disk, you're going to see a lot of radio emission because the radio waves are able to make their way through all this dust, but you're not going to be able to see the optical stuff. In that case, you're going to see a radio galaxy. But what if you're looking at it, say, from this point of view? Here you see this really, really bright region, billions and billions of kelvins all centralized in here. Really bright region. In that case, you're going to see a quasar. However, if you happen to be looking down the beam itself, that's actually a special type of object called a blazar. And there are a couple of different categories of these: optically violent variables and BL-lac objects, named after their namesake BL Lacertae. But in any case, these are all, we realize now, really the same thing. We'll have more to say about this in the galaxies unit. Anyway, intermediate mass black holes. We've talked about the little black holes, things like Cygnus X1 that are, say, a few times the mass of the sun, like dozens. And we've talked about the supermassive types that are billions or millions of times the mass of our sun, that tend to be at the centers of galaxies. What about ones in between? These are called intermediate mass black holes. They're not all that common. At least we haven't discovered all that many of these. We think that the centers of a lot of globular clusters probably have these things. There's a globular cluster called M15 in the Milky Way. That's very strongly believed to have one. It's been studied in detail, as well as a really big globular cluster, G1, in the Andromeda Galaxy. So here's a picture of M15, and there's a picture of G1. Both of these things have intermediate mass black holes in their centers. Now, what about traveling into a black hole? So just imagine what it's going to be like if you send somebody into a black hole. So we're going to consider a famous, courageous observer from the town of Beef, and his name is the famous Sir Loin. So Sir Loin of Beef approaches a black hole, and he's sending signals, say, like once every second toward observers on Earth. And at first, these signals arrive pretty much about once per second, assuming that he's a large number of Schwarzschild radii away from the center of the black hole. But as he gets closer to the black hole, Sir Loin's signals take longer than a second because of that time dilation near the black hole. In fact, the time slows down according to a faraway observer near the surface of the black hole. And if he times his drop so that he crosses the event horizon at exactly 12 a.m., then, well, we're going to see the signal that he sends at 11:59 p.m. and 59 seconds, but we're never actually going to see the midnight signal. What are we going to see for him, though? Well, remember, time stops there. We're never actually going to observe Sir Loin cross the event horizon. Now, in truth, there's something called an apparent horizon, which we do see him cross, and it's at that point where we don't actually see him anymore, but he doesn't actually cross the event horizon from our point of view. But what about Sir Loin's point of view? Now, first of all, if the black hole is less massive than about 30,000 solar masses, that's going to be real bad. He's actually going to get spaghettified. The tidal forces are going to be strong enough that he's going to get pulled apart. That would be bad. He could minimize this by curling into a ball, but eventually he's going to get pulled apart anyway. So we're going to assume we're dropping Sir Loin into a black hole that's millions of times the mass of our sun. And at least from a general relativity standpoint, the tidal forces are not going to be strong enough to pull them apart. Now, if you start bringing things like quantum mechanics into the argument, we really don't know, in truth, what's going to happen. But we're going to assume that quantum mechanics isn't important at the surface of a black hole, the event horizon of a black hole. In truth, it probably is in some way. How it's important, we're not sure at this point. But anyway, from Sir Loin's point of view, he actually does cross the event horizon. In other words, he passes right through. Everything's normal from Sir Loin's point of view, assuming the black hole is large enough that the tidal forces at the event horizon are rather small. So, as he crosses, he ends up getting all signals that are sent from Earth and everything, as well as the future of the universe, but unfortunately he can't do anything with that information. In fact, if it's a large enough black hole, then he's going to be going, well, falling at the speed of light, in fact, really along with space, at such a rate that once he approaches the singularity, by the time he starts to feel a force that is such that, like the force that you would feel by hanging from the monkey bars, the time between first feeling that force and actually crashing into the singularity and being completely destroyed would be is actually smaller than the amount of time that it would take the signals from your nerves telling you that you're feeling a force equal to hanging on the monkey bars to reach your brain. So it would actually be a painless death in that case. Another eerie result, though, if you were to analyze the Schwarzschild equation, kind of go back to that equation, remember that 1 minus 2gm over rc squared term that we kept seeing there? And once we're going to the event horizon, r is equal to 2gm over c squared. That's actually a mathematical singularity. There's also another singularity at r equals 0. That is what we call the singularity. That's a singularity that you can't work out. You can't do any mathematical tricks to get rid of that. However, that singularity that you have at r equals 2gm over c squared, the event horizon, you can do some cute little math tricks and switch to what we call Kruskal-Shakara's coordinates. And when you do that, you work in these new coordinates, and you can actually cross the event horizon using those coordinates, and nothing funny happens. You don't get any infinities, divisions by 0, or anything like that. Things just happen like normal. In other words, normal space and time, like what we think of as position and time coordinates, are not very effective coordinates for talking about things like black holes. But anyway, one of the weird results of these Kruskal-Shakara's coordinates is that when you cross the event horizon, space and time basically flip. In other words, there end up actually being multiple directions in time, and at least in a manner of speaking. But there's only one direction in space. I'll give you a moment to think about what that is. Surprise, surprise, that one direction in space is toward the center. Yet another reason why you cannot get out of a black hole, no matter how powerful your rockets are. Now, another weird result that was found by Stephen Hawking in the 1970s is that black holes can actually radiate. Think of those tidal forces. Those tidal forces can actually pull things apart. But here's the thing. Even in empty space, there's what we call this quantum vacuum, where these particle-antiparticle pairs are popping into and out of existence, and they vanish. They don't bother us because they always pop out of existence before they can be measured. This effect has been measured before, called the Casimir effect. If you put two metal plates really, really close together, these things will actually attract each other because these particle-antiparticle pairs end up popping into existence in between the small space between the metal plates, and that ends up creating image charges in the metal plates, which end up resulting in the particles getting pulled apart, and thus the plates become oppositely charged, and the plates feel a weak attractive force. That's the Casimir effect. Well, near a black hole, this effect of this quantum vacuum, so to speak, is going to be such that the tidal forces of the black hole could potentially pull these particle-antiparticle pairs apart. But these are virtual particles. They're not really there. But if one of them goes into the black hole and the other goes out, well, the one going in can't ever meet its brother or sister to annihilate, which means that that other particle is actually a real particle suddenly. Well, where did it come from? It must have gotten some energy because it can't annihilate, so it must become a real particle. That energy must come from the only thing around. That's the black hole. So we realize that these black holes actually end up radiating. These particle-antiparticle pairs that end up turning into real particles, these actually end up annihilating what's typically something else and end up simply coming out as energy, quanta of light, photons. Turns out this is actually black body radiation. We call this Hawking radiation, but from general relativity standpoint, it's a perfect vacuum. It's a perfect black body. In other words, the spectrum that you would get from just any warm object, a perfect radiation spectrum. And this is an amazing result. It shows that these black holes, even though they shouldn't be able to emit anything, there are particles coming into existence in the region outside of the black hole, and they're coming from literally the event horizon. Now, keep in mind, a small black hole is going to have large tidal forces because you can get near the center of the black hole without actually touching the event horizon. So the tidal forces there are going to be huge, but a large black hole is going to have very small tidal forces. So anyway, the result of this, though, is that the black hole loses mass because that energy, it must have come from somewhere, so it must have come from the black hole itself. So over time, the black hole is going to lose mass, and eventually it's going to evaporate. Again, it's more prominent for smaller black holes. The rate of mass loss increases with time from a larger black hole. And in the final instance, the black hole is glowing and then explodes with a sudden flash of radiation. How long does it take? Well, for our sun, it's going to take 2 times 10 to the 67 years. That's a 2 followed by 67 zeros, number of years, in order to evaporate. In fact, if you were to look at the formula for this, you find that the time goes as the cube of the mass. So a 10 solar mass black hole would take 2 times 10 to the 70th years to evaporate, and a 100 solar mass black hole would take 2 times 10 to the 73 years to evaporate, etc. The biggest black holes in the universe would take 10 to the 98 years to evaporate. That's almost 1 Google years. Googol, that is. Amazing. Now, during the final stages, this black hole's mass is decreased to a tiny amount, and it's basically something near what we call the Planck mass, and we call these things quantum black holes. It's also possible to create a quantum black hole in areas where you have extremely intense energy, like what you have in the first instance of the Big Bang. And these things, who knows, could potentially still be around if some quantum process is preventing them from disappearing entirely. But what happens is gravitons, particles that transmit the gravitational force that curves space-time, in those types of environments, they would bind together to create these quantum black holes. So we can't investigate the exact results of what's going to happen during the final instance of a black hole's evaporation, or what's going on with these quantum black holes using either quantum mechanics or general relativity. In other words, you got to use something that merges together these fundamental laws of nature. That might be superstring theory, it might be something else, we really don't know. Even if it's not superstring theory, we might be able to use superstring theory to gain some insights into these objects. Now, the fact that these things can potentially disappear leads to the information loss paradox, which was a very big deal for a long time. Here's the idea. A fundamental principle of physics says information cannot be destroyed. So let's say you get a speeding ticket and you try to set it on fire. Well, in principle, you would potentially be able to build a machine that would capture all the particles that were released from this and reproduce the speeding ticket. So you might say, well, what about information, say, like on a hard drive? So like there was a big controversy in the 2016 election, like what happened to Hillary Clinton's lost emails? Like maybe they were stolen by the Russians or whatever, but the email servers were cleaned completely. Well, this principle says that her email servers could not have been completely cleaned. That information is there somewhere. Well, what happens if you delete everything and you clean it 100%? Well, the process of deleting information from a hard drive produces heat. That heat is radiated off as blackbody radiation. And that blackbody radiation actually would have the particular photons there could potentially be used to, in principle, if you had sufficiently advanced technology, reproduce the information that was on her email servers. However, in the case of a black hole, the idea was like, well, you could throw the information into a black hole, throw the email servers into a black hole. And it's like, okay, so long email servers. Well, still somebody would be able to go into a black hole and find the email servers, at least in principle, and thus get the information. Of course, they wouldn't be able to do anything about it, but oh well. But if the black hole evaporates, and this is perfect blackbody radiation, then apparently the information could potentially disappear. This finding was found by Stephen Hawking, the person who discovered the black holes radiate in the first place, and this is known as the information loss paradox. And he actually did believe the information thrown into a black hole was truly destroyed in the end. But in the mid-2000s, well, Hawking himself actually proved himself wrong. He found that the photons could potentially be entangled in a way such that when they are radiated off by Hawking radiation, that information is encoded in the photons in some way. However, how this is done, the exact mechanism for how this is done, we really are not sure at this point. It's actually one of the biggest mysteries in physics. So if you're one of my students and you solve this mystery, then what you need to do is write up your solution and just give it to me, and I'll give you an A in the class. But it is one of the biggest unsolved mysteries in physics at this point. It probably has something to do with the fact that as the black hole is radiating energy, the black hole is losing mass. In other words, it's not perfect blackbody radiation because the temperature is not constant. It can't be perfect blackbody radiation if the temperature is not constant. And the fact that as the black hole is losing mass, that temperature ends up increasing, somehow that information is probably encoded in some way because of that. But the exact mechanism is still a mystery. So there are lots of mysteries of black holes still to be solved. Exactly what's going on at the singularity, exactly what's going on with the encoding of this information during the black hole's evaporation, those are some of the biggest mysteries of physics. And solutions to these mysteries, or the attempts at solutions of these mysteries, are driving a lot of theoretical physics right now, and the effort of solving this will probably, in the end, help to give us a unified theory of gravity. Whether that's going to happen in our lifetimes, one never knows. But once it does happen, we will have the answer to these problems. And that is the end of our black holes presentation. Thank you for watching, and if you have any questions, please put them in the comment section. Thank you.